Hello, everyone, and welcome back to HDL for Digital System Design. I'm Dr. Mike Brofchek. It is great to have you back. We're going to continue our segment on sequential logic fundamentals, and we're going to wrap up kind of how we started, talking about clocks and one of the things that they drive, which are counters. So let's dive right in. So where does this live? Well, counters exist throughout our designs. They are keeping track of baud rates. They are used to do clock division. They are used for refreshing counters when looking at DRAM. Uh, they're there when we talk about videos, pulse width modulation, watchdog timers. An SoC, a system on chip, has hundreds of counters um, operating throughout. So understanding how counters work will also lead to you understanding um, roughly, this is just an estimate, about a quarter of all digital design. Um, it is that important. So, um, we'll see this more actually coming very soon. We'll look at the debouncer in a topic coming up. We'll look at finite state machine timers. We'll also look again at UART baud rate generator. Um, yeah, a handful of things. So we'll see it in this course as well, but right now, the introduction. So um, this will probably be the first time that we go from your Verilog from written code all the way to blinking LEDs on the hardware. We've done it in little segments, but this will really be the full thing. So all the way through. One of the things to look at is not looking at counters as a loop, right? So you might think, oh, I'm going to write a for loop from 1 to n, count plus plus, and it's going to count, and the clock is going to make that loop. That's actually not what happens at all. So really much better to think of a counter being a flop, right? Um, Input is essentially, um, you know, its own output plus 1. So basically you're incrementing its own output by 1. So each clock edge captures new value, and ultimately what happens is counting occurs cycle by cycle, right? So because the clock is iterating, you are incrementing, right? It is not in the code. The code is not incrementing. It is the clock cycle that is causing that increment to happen. So there is no loop in code. It is all in hardware, right? It's just an adder that is adding, essentially feeding back into itself, um, incrementing by 1 within that space. So if you have an n-bit counter, you need n flops, all right? You also need carry cells, right? Because as you roll over, you need to carry. So you need n flops and you need n LUTs and carry cells. So it's a actually fixed footprint. You know exactly what size you need based off of the size of your counter. So basically the other thing is counts to 2 to the n minus 1, right? Any n-bit counter will count to 2 to the n minus 1 and then roll over to 0, right? So to count to 2 to the n, since we start at 0, you basically are getting 2 to the n minus 1. You actually saw that pattern in our very first video in this series. So essentially that value of count will keep changing because the clock keeps triggering, right? That clock stops, so does the counter. So has nothing to do with code running. It is all about the fact that your hardware, that clock signal keeps coming in, triggering the addition of an additional bit into um, basically into the next flop. Okay, so so first off, let's just look at a free running counter. I have a register called rcount. I then have an always block that is positively triggered on the clock. And I now also, bringing in from the last video series, if I have a reset signal, I'm going to reset my count to 0. Otherwise, I'm going to increment my count by 1, right? So what you basically see here, assuming, of course, that I am not in reset cycle 0, my count is going to be 0. In cycle 1, it'll be 1. In cycle 255, it'll be all 1s, or in hex FF. And then at the very end, one more added to that, it's going to roll over to be 0, 0. So the three big elements in here that I think about are: one, you need a register to declare where you're going to store, right? What is the, where's this counter going to live? And so for us, that is our count here. You need to have a sensitivity trigger on the clock. Again, this is positive edged triggered. I've alluded to it in a handful of other lectures. There's also, you could do things negatively edged, right? So on the falling edge of the clock. Um, but in this particular case, we have positive edge triggered, and you basically get, whenever you're in this state, you're going to increment our count by 1. We basically get rollover for free. Notice we're not doing any logic in here to rollover, because we have an 8-bit value at 256. When we hit 256, we essentially roll over. That extra bit goes away. Essentially, there's nowhere for it to go, because we're not storing it. So that's the reason why we roll over, is essentially we've exceeded on that last uh, carry. There's nowhere to carry to, and so the remaining lower 8 bits, the 8 bits we have, are all 0. That 9th bit would have been a 1, but we're not storing it, so free rollover here. Okay, so together, we kind of saw this already in a very limited form, but here we go again. Notice the pattern. We're going to build clock division. We're going to go from 25 megahertz clock down to 1 hertz. So we have a counter here, and you'll notice that the way that we're going to do this is we want 1 hertz blink. It's toggling every 12,500,000 cycles. So if we look at 1 hertz period, 1 second equal 2 half periods of 50 milliseconds each. If we look and we take the log essentially of 1 million, well, 12,500,000, that is actually 24 bits that we need. So that's why we have a counter that is that size. We have our LED that we are going to blink, also as a register internally here. You'll notice at the very end of this code, we're tying that out. We're tying our register value out to our LED 1. But internally, what are we doing? Well, on our reset has essentially set counter to 0 and LED also to 0. This reset is important just to have a reset state when starting up. But in normal operation, what we have is if the counter hits essentially 1 less than our target, right? Because we're counting from 0, so 12,499,999. If we hit that, we're also going to reset our counter, but we're also, very importantly, going to toggle our LED. So LED toggles here. In normal operation, what are we doing? We are counting. We are just incrementing our counter by 1. All right. So if we have essentially 1 hertz cycle for a LED, basically what we're really saying here is it should spend, an entire cycle is 1 second long, which means it's going to spend half a second on, half a second off. So basically, we can do this. 25 megahertz clock. Ticks is basically, like we computed here, 12.5 million. So we toggle every 12.5 million cycles, and ultimately we can fit this in. 24 bits holds up to 16 million. We're okay. You can do the math, figure out that 23 bits would not be enough. It would be roughly half that value that we could store, about 8 million. So, all right. Okay, so can you do it? Can you follow the same pattern we just did and come up with a 4 hertz blink? So 4 hertz blink, we would want half of that time, right, is going to be spent on, the other half off. So that's the hint there, much like we just did here. 1 hertz blink, meaning half of the time is spent in off, the other half is spent on. So same thing here. Can you do it for 4 hertz blink? Go ahead and give it a try. And I will leave this up while you pause the video, and see if you could figure this out for 4 hertz. Okay, welcome back. Let's see what this looks like. So 4 hertz means that you need basically a 0.125 second half period. So if you take your 25 million clock ticks, multiply that by 0.125, you get 3,125,000. So that means you need to toggle every 3,125,000 cycles. You can do this count. 24 bits here, but you could actually just do it in 22 bits, right? You don't need the full 24-bit range like we did in this prior example. You could do it with less bits. You might ask yourself why you might actually retain a full 24-bit value, but we'll get there. So you could do it in 22 bits. And just a quick follow-up here. If you take any frequency that you want, right? So we said 4 hertz here. You can take any frequency you want and make this parameterizable. So I'm giving you a kind of a sneak peek for a future topic here, but this is something that we could do. Okay, so um, we could go ahead and do this. We can go to our board and we can do an example. We'll do this is week 1, day 4, example 3. So let's just let's do it. Let's open up our terminal and let's get to the right location. All right, and we're gonna just we're gonna make program here, and let's switch so that you can see the device view. All right, there's a lot going on here, but what I want you to look at is just the first LED here. And notice that it's blinking at a rate of basically 1 hertz on and off within 1 second time period. We should get an oscilloscope on here to verify that. But for now, just you can time it, use a cell phone if you'd like, just to see that that is blinking at 1 hertz. Now, there are a lot of other LEDs there blinking right now, but we're going to see why that actually is. And actually, we might as well take a look. So this, I guess, is a sneak peek of the future, but essentially what we're getting here is, let's pull up that code for you. So if we take a look at the LED blinker, and we're looking at output 1, right? So we're looking at what we care about for LED 1 right here. It's the one that we're looking at. What we see here is exactly what we built. The reset isn't in here just for simplicity, but we're essentially counting to that right under 12.5 million, and we are blinking, right? We're swapping that value of the LED and doing the increment otherwise. So that's just that code straight through. So can easily change this, right? If we wanted to change this to the other value, right, that we just saw in our example. So the prior value was 3, let's see, 3,125,000, I think was the frequency. So we could change that real quick. 3,125,000. But we need one less than that, right? So 24,999. I'm not even going to change the size of this because it doesn't make a difference right now. Going to change that. And while it would be nice if I could come in here and do a make directly in this terminal, actually, let me show you that you can do this. So depending on what version VS Code you have and other things, you might be presented with an option to run Verilog code. Depends on what extensions you have. This is probably not going to work as expected immediately. mostly because it's not going to be pulling from the right location for all of the tools we need. So what's actually easier, I think, in this particular case, is you can hop over to your terminal, and as long as you are inside the very top level of the terminal, inside of the directory structure where all of this is located, you should be able to type in nix develop. And let me clear this out just so it's at the top and you can see it. So you should be able to do a nix develop, and it will run through the actual environment setup. You'll have access to all the tools that you had everywhere else, but only within this particular space. So what you need to do is you need to still change directory to our lecture examples, week 1, day 4. And this is, again, day 4, sample segment 4, I believe. So when you're in here, or in the exact same locations, you can run a make here, and it will work as expected. So type in make, it will make it, but you can also do a make program. And what we should see over here, all these are still going to go off, but notice that our blink is now at 4 hertz. It is double. That is blinking on and off twice within a single cycle. Actually, we said 4 hertz, so actually that whole cycle 4 times, right? So much, much faster. Okay. Now, we'll talk about the other LEDs and what they're doing here in a moment, but for now, that hopefully provides you a bit of proof and evidence that code that we change here can go through the whole cycle and send it all the way to our device. Okay, so let's continue on, and let's make sure you can see it. All right, so we just saw it. Yeah, all right, so our tool ended up building a handful of flip-flops, handful of LUTs, and it needed carry chains for what we built. Now there's some other code in here, so it's not exactly one-to-one mapping. You can strip out the other code, the other logic that's been built out to see what would be built just for the single counter. Now, we do have an explicit counter that I showed you, and then we actually have another one that we'll show you here in a few moments that is actually free running counter, and we're just observing certain bits, which is a kind of a really neat way to access, well, access when a certain frequency is occurring just by observing individual bits. So just to think about this, a 32-bit counter would be basically 32 flops and 31 carries. It's not that big. So you can host a handful of independent counters at the same time in a design. It's why and what actually happens in devices that have multiple peripherals operating at different speeds. This happens all the time. So what I'm going to revisit for a moment is actually a super quick trick, like just I'll say a trick, but really it's more than that. It's commonly used. You can imagine that I have a counter that's running, and it is, we've already established it's running at some frequency, some rate. Well, just observing specific bits in my counter would allow me to basically immediately get different frequencies for free, right? So if I have a 24-bit counter and I know that its approximate frequency there is listed, I basically know that each bit below that, right, is essentially a doubling or so of that frequency. And so it's actually a super nice trick to do. And so down here, I've got the quick trick. You can use a free running counter and basically figure out approximately how fast things are running. So the nth bit of a counter is essentially the frequency of the clock divided by 2 to the n plus 1. Right, so there's an approximate in here because essentially that plus 1 is not taken into account. We normally subtract out when we're doing that, the clock computations, we'd subtract that 1, right? So we aren't checking for example, 12.5 million. We're looking at 12,499,999. We're not able to do that in this particular trick, but what you still see here is pretty quick way to get approximate frequencies very easily here. So this will only give you power of 2 divisions though, right? If you have a frequency that is not a nice power of 2, right? So UART would be a good example of that. Sampling audio rates, you'll need to do what we've done in the past, which is essentially do exact computations. So you can use bit taps for LEDs, but if you have specific targets that you have to hit that are not evenly divisible by 2 powers, you're kind of out of luck. Okay, so something you can do, you can design a clock divider to produce a 9600 hertz output from a 25 megahertz input, write parameterized Verilog. So you could ask an AI to do this. You can do the prediction on what you expect to see, about 11 bits for your counter, and also the target count. If the AI is good, it's going to create you a parameterized version of this, which then would allow you to change that frequency if you needed to. Otherwise, you're probably going to get a hard-coded target. So yeah, so we're going to see this in topic 11. And so one last thing before we actually hit the key takeaways, I'm going to show you those bit taps because that is what is running right now on the device on the last 3 LEDs there. So the bit tap here, we have a second. So we have a second register here that we've defined just again to show you. So second register here, 24 bits. And all we have here is it's just free running. There's no other logic. It is just a free running counter. No resets, doesn't do anything. It will just run to the maximum value and it will then roll over once it hits. And so the rollover is important here. But what you basically see here is we have LED 2, 3, and 4. And all we're doing is we're looking at this free running counter. We're looking at these individual bits here. And that essentially maps every one of these is a doubling of frequency. So that's what we have. All right. Okay. So wrapping up here, the key takeaways for this segment. Counters exist throughout all sequential building blocks, right? If you have an n-bit counter, it rolls over every 2 to the n cycles. Clock dividers, you're going to count to a target, toggle when you hit that target, and reset. If you need it, right? If you are looking for, I'll say, some approximate frequencies, right? Or things that are not specific to a protocol where you have some leeway, using significant bits or using the bits you care about within a counter is a really nice approach. So these are basically bit taps. So here you go, counter plus comparator plus toggle equals any frequency you want. All right, so this should work anywhere you need it. All right, so a little self-check across all these segments. What happens if you use basically a blocking assignment instead of a non-blocking assignment in a sequential always at positive edge block with 2 registers? What's going to happen? What is the behavior that you expect? All right, write a D flip-flop with synchronous reset from memory. Can you do it? All right, number 1, both registers would get the same value in 1 cycle. Right, the blocking assignment updates immediately, and the pipeline behavior gets destroyed. Saw a couple diagrams of those. All right, here's that D flip-flop. Essentially, you have if reset, set it to 0. Otherwise, set the output to the input. Again, those less than or equal signs should be split out there. Okay, next. if a missing else in an always at positive edge clock, do you get a latch? So is that true? And you want a 2 hertz blink from 25 megahertz. What do you count to? So that might take you some time. So pause this video for a second, see if you can answer that. So first answer, no. Flip-flop already holds its value. You don't need, it's not going to create a latch. That only happens if you're talking about an always block with wildcard sensitivity, right? Where you're building combinational logic. If you don't cover your branches in that space, then you will get a latch. But when we're talking about sequential logic, there's already this idea of holding on to your value. A flip-flop will hold on to its value. There's not a latch that's produced in addition. All right, the last one, which takes a little bit of math. So 2 hertz toggle means that you're toggling every 0.25 seconds, every quarter of a second. So that is essentially 6,250,000 cycles per half period, which means you've got to count to one less than that, 6,249,999 that you're going to toggle and reset. So that's your count, that's your target. All right, so what are we going to cover next time in the next set of sequences? If you've done this in a week, what are you covering next week? Patterns and verification. So we're gonna look at more counters. We're gonna look at test benches, finite state machines, and hierarchies. Right. So far everything we've done has been essentially one module. Using that one module, we haven't started to build up our modules. But what can you do now that you couldn't do at the beginning? Well, you probably have the vocabulary of single module RTL. You know what modules are, you know about data types, operators, combinational blocks, sequential blocks, flip-flops with reset and enable. You also know about counters with clock division. We're going to build on all that, looking at counter variations, shift registers, test benches, finite state machines, and again, module hierarchy. And so by the end of next week, you'll be composing and building multi-module designs. So with that, thanks for watching, and we'll see you next time. You've got plenty of things that you can now use to build some cool stuff. So go build cool things, and we'll see you next time.